Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 4, Lesson 6 on exponential modeling based on percent growth and decay. Much of what we're going to do today should be a review of some of the work that you did in Algebra 1 with exponential modeling. But of course that was a couple years ago, especially if you took geometry last year. So let's jump into it right now. Developing an increasing exponential model. Exponential functions are important in modeling many real-world phenomena because certain things either increase or decrease by fixed percentages over given units of time. You looked at this in Algebra 1, and in this lesson we will review much of what you saw. So let's jump in to exercise 1. Suppose that you deposit money into a savings account that receives 5% interest per year on the amount of money that is in the account for that year. Assume that you deposit $400 into the account initially. Letter A, how much will the savings account increase by over the course of the year? All right, well this just has to do with, do you understand how interest works? All right, how do percents work? Pause the video now. You're going to want a calculator throughout this lesson and see if you can figure out how much simply the savings account increased. Not what it was worth at the end of the year, but just how much it increased. Pause the video now. Well, essentially what we're asking you to do, right, is we're asking you to find 5% of $400. Now, hopefully all of you remember that the simple way of doing that is to take 0.05 and multiply it by 400. And of course, that's where we might want our calculator, right? We just take this out. Let me clear all of this out. And we just take 0.05 times 400 and we get 20, right? Simple enough. So that's going to increase my account balance by $20. Awesome, free money. All right, let's take a look at letter B. How much money is in the account at the end of the year? Well, this is pretty easy, right? That's going to be $400. Let's not even have you do this on your own. Plus $20. So that's going to be $420. Now here's the thing though. We don't want to have to do this and then do this, all right? And the reason we don't want to have to do that is not because that was particularly difficult, but because if I asked you, well, how much would the account be worth after 20 years? You'd then have to take 420, multiply it by 0.05, get a value, add it to 420. That's what we would have at the end of year 2. Then we'd have to take that amount, multiply it by 0.05, get another amount, add it to whatever that was. That's what we'd have at the end of year 3, et cetera, right? And we wouldn't want to do that. That would be like 40 calculations just to figure out how much we had at the end of 20 years. So let's take a look at letter C. By what single number could you have multiplied the 400 by to calculate your answer in part B? So in other words, I don't want to do this two-step process. I want to do a one-step process. And of course, we can figure that out by maybe just setting up an equation, right? Like I'm literally asking you, if I did like 400 times r, or maybe I'll just have 400 times x equals 420, then what is x equal to? Well, pause the video and figure that out. All right, well, and hopefully what you found was not much of a surprise. In fact, hopefully you could have done this right from the beginning, 420 divided by 400. So we just do 420 divided by 400. Now that's going to give me a reduced fraction, so I have to do that, and I get 1.05. 1.05. And that is not a coincidence that I've got 0.05 up there and I've got 1.05 down there. Because in reality, what's really going on, right, is that this calculation is 400 plus 400 times 0.05. So that's 400 times 1 plus 0.05. And that's 400 times 1.05. So to increase something by 5%, we're going to multiply by 1.05 so that we get the 100% that we started with plus an additional 5%. Now here's why that's so useful. Let's take a look at letter D. Using your answer from part C, determine the amount of money in the account after 2 and 10 years. Round all answers to the nearest cent when needed. Well, for 2 years, right, we get to multiply 400 by 1.05 twice. In other words, we get to multiply 400 by 1.05 squared. So 2 years, that's going to be 400 times 1.05 to the second. And 10 years, that's going to be 400 times 1.05 to the 10th. So why don't you go ahead and figure out what those two values are? Pause the video now. Awesome. Well, let's take a look. I'm not going to break the calculator out because that should be easy enough to plug in. What we find is after 2 years, it's actually an exact amount, $441, and after 10 years, we do a little rounding. That ends up being 651 point, sorry about that, a little tight, 651.56, and let me make that look like a dollar sign. Okay, now all of this then allows us to finally create an exponential model. All right, let's take a look at letter E. Give an equation for the amount in the savings account S of t as a function of the number of years since the $400 was invested. Well, this is great because this is a classical exponential equation, right? The savings will be our y-intercept, our original amount, times our base, 1.05, raised to the number of years that I've applied it. 400 times 1.05 to the t. So after 2 years, I've gotten to multiply my 400 twice. After 10 years, I've gotten to multiply my 400 10 times by the number 1.05. Every time I multiply by 1.05, I increase what I had the previous year by 5%. Let's take a look at letter F, where we're going to do a little calculator technique. Using a table on your calculator, determine to the nearest year how long it will take for the initial investment of $400 to double. Provide evidence to support your answer. All right, now in this case, we're going to use a table on our calculator, but we could use a graph just as easily, and we will later on in the lesson. And eventually, in our next unit, we'll actually see how to do it algebraically. But ultimately, right, what we're trying to do is we're trying to figure out when 400 times 1.05, and let's call it to the x maybe, is equal to 800, right? And we want to figure out that to the nearest year. So let's break out our calculator and take a look at a table. Let me just kind of go in here, new document, no. Let's bring out a graph. All right, so I'm going to put in 400 times 1.05 raised to the x. All right, and of course, I don't see anything because my window is wrong. Everything's just wrong about this, but I don't even need a window. What I want is my table, so I'm going to go Control-T to enter a table. And it does nothing because apparently I didn't actually get my function in there. Let's try it again. I'm like, where did it go? I was wondering about that. 1.05 raised to the x. Let's try it again. All right, now let me do Control-T. There it is. All right, and in fact, just for a moment, nope, stop that. Sometimes my calculator has sort of a mind of its own. We can actually already see that after 0 years, right, the y-intercept, we have 400. 1 year, 420. 2 years, 441. There's that 2 years at 441, right? And we see it kind of going up. Now remember, we're looking for it to double. So I just kind of continue to scroll, whatever, through. And I finally see, let me just kind of move it up a little bit. After 14 years, we're at 791.97. And after 15 years, we're at 831.57. Now, it kind of seems very likely, of course, that the answer to the nearest year is 14. but I might want to get that a little bit more refined. So here's some calculator technique for you. All right. If I come over into my table and I go to menu, I don't have very much in terms of a menu when I'm in my table. But I'm going to go into my table and I'm going to go down to Edit Table Settings. I'm going to make my table start at 14. But instead of my table step being 1.0, which means that it goes from 14 to 15 to 16 to 17, I'm going to make my table actually go by tenths, 0.1. So now I'll get to see what does this function equal at 14, what does it equal at 14.1, 14.2, 14.3, etc. So if I hit enter on that, now what I see is at 14, we're at 791, 14.1, 796, 14.2, 799.7, and 14.3, we're at 803.65, right? That tells me definitively, so if I did like a little table here, and then of course I lose everything that I want, but if I do like a little table there, what I see is that at 14.2, no decimal place there, at 14.2, I have 779.4, whereas at 14.3, I don't think that's quite right, I have 803.65. Let me just look at this. 14.2, I have not 7, I have 799.4. And that's enough evidence now for me to know for certain that it's closer to 14 years than it is to 15 years, right? In fact, sometime between 14.2 years and 14.3 years, I've doubled. So to the nearest year, X is going to be 14. I wanted to take that opportunity to show you how to set up a table on the TI Inspire and then refine the table so that it went by tenths in the X values instead of just whole number ones. All right. Let's go back into our full screen and let's generalize. General equation for increasing exponentials. The thought process from exercise number 1 can be generalized to any situation where a quantity is increasing by a fixed percentage over a fixed interval of time. This pattern is summarized below. So let's kind of like take a look at the pattern. Exponential models based on fixed percent growth or increase. If quantity Q increases by a fixed rate R over a unit increase in time t, then Q can be modeled by Q of t equals Q sub 0, right, the y-intercept, what you begin with, times 1 plus R raised to the t, where Q sub 0 represents the amount of Q present at t equals 0, and where R is equal to the percentage divided by 100. Now again, just to be very clear about this, right, I'll oftentimes talk about the decimal version of a percent. That's what's known as the rate. So in our last problem, right, where we had 5%, R was 0.05. It was 5 divided by 100, 5 100ths, all right? So we're never adding the percent here. We wouldn't want 1 plus 5. We have 1 plus 5 100ths, all right? That's all we're talking about here. Now, the other thing, though, I do want to point out is we're talking about a per unit increase in time. So in other words, they're going to tell you that something is increasing per year, per day, per second, per minute, not per 5 days or per 2 years or per 8 seconds, right? It's always a percent increase in a unit amount of time. 1 unit, 1 second, 1 day, 1 hour, 1 year, something like that. So let's take a look at exercise number 2. A savings account has $250 initially deposited in it. The account earns an interest rate of 3.5% per year. Assuming no further money is deposited, create an exponential model for the amount of savings S as a function of the number of years since the initial deposit. Then use your model to predict the account's worth after 10 years. Oh my goodness. Okay, well, what I'd like you to do is pause the video now and see if you can set up the exponential model, and then also see if you can use it to predict the account's worth after 10 years. Take a few minutes to do that. All right, well, again, just to be very clear, right, our rate, the thing we're going to add to 1, is 3.5 divided by 100. Move that decimal place 2 units to the left, right, and we get R is 0.035, right? R is not 3.5, it's not 0.35, because 0.35 would be 35%, and that would be wonderful interest, but you're not going to get it on a savings account. So our model now, S of t, will be the amount we start with, 250, times 1 plus 0.035 to the t. I would suggest not leaving it like that, and maybe rewriting it as 250 times 1.035 to the t. So there is our increasing exponential model, right? And we know it's increasing because our base is greater than 1. If we just put 0.035 in here, that would be a decreasing exponential, which we certainly don't want out of a savings account. We don't want to put money in a savings account and have it go down over time, right? That wouldn't be good. And again, it's because we're adding it to the number 1. The 1 gives us the 100%, and the 0.035 gives us an additional 3.5%. Now let's use it to figure out what S of 10 is. Again, that's easy enough because we're just going to be substituting this into our calculator. Should be no issue. We just kind of crank through it. It is kind of messy, whatever it is. It's 352.6496, etc. And that's going to be $352.65. All right, easy enough. And pretty much all exponential models that are based on percent growth can be done just like this. Come up with the rate, again, most of you probably won't even have to write this step out. You'll just be able to say, oh yeah, sure. 2.75% is 0.0275, right? Just move your decimal place 2 places to the left and you're going to be all set. Add that to the number 1, that is your base, right? Your y-intercept is whatever you started with, whatever was initially deposited, or your original population, or whatever it is, then raised to your x, your t, or whatever. Now, we want to also be able to deal with decreasing exponential phenomenon, so decreasing by a percentage. Decreasing exponentials are developed in exactly the same way, but have the percent subtracted rather than added to the base of 100. All right? You are always, by the way, multiplying by the percent in decimal form that you will have after the time period elapses. Okay? So just to kind of emphasize that, exercise number 3. State the factor, the base, you would need to multiply by to decrease a quantity by the given percentage listed. Now again, the idea is, if I was decreasing by something by 10%, right, then what would happen is I would have 90% left over, right? That's what would remain. But what I would actually want to be multiplying by is 0.9. And maybe I'll put it as 0.90 to just really kind of hammer home that idea. All right, so if I want to decrease by 10%, then I'm not going to multiply by 0.10 or by 1.10, but I'm going to multiply by 0.90 because that is the percent that I have remaining after I've done the decrease. Likewise, if I was decreasing by 2%, all right, then I would have 100% minus 2%, which would be 98%, and that would mean I would want to multiply by 0.98. All right, very, very simple. So pause the video now and see if you can do the remaining 2. All right, letter C I'm sure is quite easy, right? If I'm trying to decrease something by 25%, all right, what I have remaining left over is 75%, so I'm going to be multiplying by a base of 0.75. Now this might be the most difficult, right? If I'm decreasing something by 0.5%, 0.5%, then what I'm going to have left over is going to be 99.5%, which means the base is going to be 0.995. That's what I'm going to want to multiply by again and again. Now we can kind of generalize all of this just as we did before, and let's take a look at the general decreasing model. We can now look at the general model for a decreasing exponential function based on a fixed percentage rate of decrease, which is sometimes also known as decay, especially when we get into what are called radioactive decay. So let's take a look. Exponential model based on fixed percent decay, parentheses decrease. If quantity Q decreases by a fixed rate R over a unit increase in time t, then Q can be modeled by Q of t equals Q of 0 times 1 minus R to the t, where Q of 0 represents the amount of Q present at t equals 0, and where R equals the percentage divided by 100. Now, if you compare this to what we had in the box on the front side of the sheet, the only difference you'd see is 1 minus R compared to 1 plus R. All right? It's the only difference, right? In one case, you're adding the rate on, the percentage in decimal form. In the other case, you're subtracting the rate, again, the percent in decimal form. So let's look at a decreasing exercise. Exercise number 4. The population of a town is decreasing by 4% per year and started with 12,500 residents. Letter A. Write an exponential model for the population, P of t, of the town as a function of the time in years since it was 12,500 residents. Great. All right, so let's do this one kind of together. First thing I just want to think about is the rate of my decrease, right? And that's 4 divided by 100, and that's 0.04. All right. Now, according to my general model, my population should be what I'm starting at, 12,500, times 1 minus 0.04 to the t, which means my population will be 12,500 times 0.96 to the t. And again, just kind of looping back on our previous exercise, the idea is after 1 year, we have 96% of the population we started with. And then 1 year after that, we have 96% of the population we had at the end of, the first year. And then 1 year after that, again, 96% of the population we had of the previous year. Each time, right? We're taking 4% away from 100% and being left with 96%. Now, letter B should be pretty easy. Use your model to predict the population a decade since it was at 12,500 residents. All right, well, what I'd like you to do is pause the video now. You'll definitely want to use your calculator and use this to predict the population 1 decade after we were at 12,500. Well, obviously 1 decade is equal to 10 years. So we just want P of 10, which is going to be 12,500 times 0.96. We get to multiply by that 0.96 10 times. All right. And we can find, it's kind of messy again, as many of these things are, 8,310.407, etc. Now we're talking about the population of people, so we can't have a decimal there. So rounded to the nearest person, 8,310. All right, great. And again, this is just calculator work, just typing this expression in. So we're not going to break the calculator out for that. Let's do one more problem. All right, exercise number 5. The stock price of Wind Power Inc. is increasing at a rate of 4% per week. Its initial value was $20 per share. The stock price of Gerbil Energy is crashing, losing value, at a rate of 11% per week. If its price was $120 per share when Wind Power Inc. was at $20, how many weeks will the stock prices after how many weeks will the stock prices be the same? Model both stock prices using exponential functions, then find when the stock prices will be equal graphically. Draw a well-labeled graph to justify your solution. All right. Well, what I'd like you to do is pause the video right now, set up the 2 exponential models for both wind power Inc. and gerbil energy. Get those two functions down. One's going to be increasing, one's going to be decreasing. And then see if you can use your calculator to come up with a graphical solution for when the two were equal. Now, it didn't say what to round to. I think I'm going to end up rounding to the nearest tenth of a week, although the problem didn't really specify that. So see what you can do. All right, well, let's start with Wind Power Inc. All right, it's increasing 4% per week with an initial value of $20. I guess maybe I'll call that W and I'll do it of T. So my initial value is 20. It's increasing at 4% per week, so that would be 1 plus 0.04 or 1.04 raised to the T. There we got wind power. Let's see. Gerbil energy, right, which obviously is crashing because gerbils can only run so fast for so long. But we start there with 120. It's losing it at 11% per week. So that means our multiplier is going to be 0.89, 89%, right, is going to remain each week. So these are our two functions, right? They're the two functions that are modeling their relative values. And ultimately what we want to do is we want to solve this equation. I'd love to use the method of common bases that we saw in a recent lesson, but I'm pretty sure it would be difficult to figure out a common base for 1.04 and 0.89. Therefore, I can't really use it. But we can certainly use our calculators, and we're going to be doing that a lot in the next few lessons until we get to the next unit where we have more concrete algebraic techniques for solving something like this. So for right now, what I'm going to do is I'm going to graph the left-hand side, I'm going to graph the right-hand side. We're going to figure out where they intersect. Let's do it. Let's get a nice graph for this. I'm going to go open up a brand new file. All right, let's add a graph. And I think I'm going to put wind power in my first one, so that's going to be 20 times 1.04 raised to the x. All right, in F2, I'm going to put in 120 times 0.89 raised to the x. All right, now I've got my 2, and I see absolutely nothing on my screen. Kind of makes sense, right? Wind power is starting at 20 and going up. Gerbil Inc. is starting at 120 and going down. So my Y window, which only goes to like 6.67, what a weird window, only goes up to 6.67, is not even getting like the minimum value of this thing. So let's do this. Let's go into our menu and let's work on our window. Okay, I'm going to go into my window settings. Might as well start with X-min at 0. I don't know how big X max is. Maybe 10 is fine, so I'm going to leave it alone for right now. But one thing I know for certain is I'm not going to have any minimum values that are negative. And my Y max, I mean, I started 120 on gerbil power and then I decreased. So maybe I'll put my Y max at 150. Okay, now that's a lot better, right? Because here I'm looking at my gerbil power starting at 120 and decreasing. I'm looking at my wind power Inc. starting at 20 and increasing, although pretty slow. And they're getting pretty close out here, but they do not quite intersect, which means I've got to make my X window a bit bigger, right? And that sometimes just happens. We could look at a table to try to get a feel for it, but I'm just going to play around with the window. I'm going to go into my window settings again, and maybe instead of 10, we'll go 20, right? Remember, these are weeks. All right, and when I do that, let me just move these things out of the way a little bit so that we can see the graph a bit better. Now I see my intersection point, right? I can see here is my wind power, here's my gerbil power, and they're going to intersect right there. So let's now use the intersect command to figure that out. I'm going to go into menu and I'm going to do analyze my graph. I want intersection. I'll bring that vertical line there. Scoot it over there, hit enter, bring that up like that, and what I end up seeing is that they intersect exactly, which is kind of great, at 11.5 weeks and $31.4 per share. Now, they do say draw a well-drawn graph to, sort of make this look right. So what I'm going to do, I'm going to go like this. I want to write down my scale, right, t. I think I had this at, what was my maximum? It was up there at 150. Okay, we had that was our gerbil power, so I can just say g of t is equal to 120 times 0.89 to the t. Then we had our other one, which was wind power, and that was 20 times 1.04 to the t. And then we had them intersect at 11.5 comma 31.4. And so I can now say, right, that t equals 11.5 weeks. That is when the two are equal to each other. When you don't have an algebraic technique for solving an equation like this, it is always then fair game to graph the left side, graph the right side, and use your intersect command to solve the equation. Plus, this really gives us a great sense for it, right? Because we've got Gerbil Power Inc., its share price is decreasing. We have wind power, right, going up. And it's kind of cool because obviously where the two graphs intersect is where their share prices are the same. And that happens after 11.5 weeks. All right, let's wrap this up. So today, we really reviewed, for the most part, how to construct increasing and then decreasing exponential functions based on percent growth and percent decrease or decay. All right, that comes up a ton in the real world. Like you will see all the time something like, oh, the population of New York City is growing at 2.5% per year, or the population of Charleston, Illinois is decreasing at 5.25% per year. You see things like that all the time. A fixed percent growth or decrease over a fixed interval of time. So it's important to be able to come up with exponential models for things like that very quickly, because those will be exponential as opposed to, let's say, a linear model, which we saw a few units ago. All right, well, we're definitely going to work with these more in our next lesson when we do more exponential modeling. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.